Hey everybody. Okay, so we were talking in the last lecture about how low mass stars and intermediate mass stars evolve off the main sequence until they inevitably die as a planetary nebula and a white dwarf. How do high mass stars evolve? And then how do they die? Well, the lives of high mass stars are actually a little different than low mass stars like the sun. So we were talking before about how the sun generates power via hydrogen fusion in what's called the proton-proton chain. High mass stars still fuse hydrogen during their main sequence lifetimes, but they do it by a different set of reactions, what's called the CNO cycle. So basically, it works like this. We'll go through the long way and then we'll simplify it here in a second. In the core of a high mass star, yes, it's mostly hydrogen with a lot of helium, but also there's a little bit of carbon, nitrogen, and oxygen. And the carbon, the nitrogen, and the oxygen can act as catalysts to promote the hydrogen fusion happening faster and producing more energy on the output. A low mass star like the sun can't do that because the core of the sun isn't hot enough. But in a high mass star, the core temperature is hot enough that you can take a carbon atom and fuse it onto a hydrogen atom. And when carbon-12 fuses onto a hydrogen, it produces nitrogen-13 and also produces a gamma ray. So we're already at step one and we're already producing energy. So that's pretty convenient. Nitrogen-13 is unstable, and so it will decay and turn into carbon-13 and do that by emitting a positron and a neutrino. Should sound familiar by this point. Carbon-13 is pretty stable, so it will hang around for a little bit until it fuses onto another proton, which turns into nitrogen-14, which is stable, and also produces another gamma ray. The nitrogen-14 will fuse to another hydrogen, produce another gamma ray. That becomes oxygen-15, which is unstable. It decays into nitrogen-15, emits another gamma ray, another positron and another neutrino. And then the nitrogen-15 fuses onto another hydrogen, where that produces helium. That helium splits off from the, let's see, nitrogen plus another proton makes it oxygen. So the oxygen-16 splits in two, where the helium splits off, and you get your original carbon-12 back. So that this is a hydrogen fusion reaction, and just like proton-proton chain, you take four hydrogens, you fuse them together, and you produce a helium. But the carbon, the nitrogen, and the oxygen are acting as basically sites. They act as catalysts that the hydrogens slam onto to help the hydrogen fusion go faster. And in doing so, you produce, when you take the four hydrogen and turn it into one helium, you get three gamma rays out, instead of just the two gamma rays that you got from the proton-proton chain, as well as the positrons and the neutrinos. So, because these high-mass stars are hot enough in the core to undergo CNO cycle burning, they can burn their hydrogen faster, which is how they have a higher fusion rate, which is how they're able to maintain 10,000, 100,000, a million solar luminosities during their lifetime. This is also why they burn out so fast. These stars burn out in just a few million years, as opposed to lasting 10 billion years like the sun will. When those stars, very quickly, run out of hydrogen, they do something similar to what the sun will do. They do something similar to what low mass stars do. They expand, they cool off, and they become red supergiants. but it's not quite as dramatic as a low mass star, right? A star like the sun will puff out and go up the red giant branch until there's that flash of helium igniting, and then it settles into the horizontal branch. These high mass stars are already so big, so high mass, so hot on the inside that the transitions here become almost anticlimactic. That these high mass stars will expand and become red supergiants, and as for the same reason that the low mass stars become red giants. That helium core contracts down and heats up, and it comes over here until the helium ignites, and then when the helium ignites, that star is able to reheat and become a yellow supergiant or a blue supergiant for a little while. It's almost ridiculous. It's almost comical that the core of this star contracting down and heating up to 100 million Kelvin. Well, these stars are already so hot on the inside that reaching 100 million Kelvin and then the helium igniting is almost anticlimactic. It's like, oh, no big deal. I reached 100 million Kelvin? No big deal. And that's why the luminosity doesn't change that much. The luminosity doesn't change. It just kind of expands and cools off, but the energy production rate stays pretty much the same. So it burns. So it wanders into the middle of the supergiant branch during the helium burning phase until it burns even more quickly through all of the helium in the core. So then things start evolving very, very quickly, right? So the inside of a supergiant is kind of like the skin of an onion. It has layers inside of it, and so while that star is a main sequence star, you've got hydrogen fusing into helium in the core, and then you've got the outer layers of the star are just inert hydrogen burning in the core, and just hot hydrogen in the rest of the star. That's the main sequence. And then the hydrogen runs out, and that helium core shrinks, it contracts down, and it heats up to 100 million Kelvin, and it starts fusing helium into carbon. And then you've got that shell of hydrogen burning right on top of that. So far, pretty much like a red giant, and a horizontal branch. Unlike a low mass star, though, once all of that helium burns into carbon, then the carbon core contracts down under gravity. It goes over 1 billion Kelvin, and it's able to start fusing the carbon in the core, starts fusing into neon and sodium and magnesium. And on top of that, you've got a layer of helium burning into carbon. And then on top of that, you've got a layer of hydrogen burning into helium. And all 3 layers are now radiating more heat into the rest of the star to maintain that luminosity. And then once the carbon runs out, that carbon has fused into neon. And then the neon core shrinks down, heats up even more until the neon becomes so hot that it's able to fuse into stuff like oxygen and magnesium. And then once the core has converted to being completely oxygen, then the oxygen core shrinks down, heats up, until the oxygen is able to fuse into silicon and sulfur. And then once the core has become completely silicon and sulfur, then the silicon and the sulfur start slamming into each other to fuse and create things like iron and nickel. And this is the last step. Because once the core of that star has completely converted into iron, all the nuclear reactions in the core stop. Iron is the last element that the core can fuse into and still actually produce energy. Let's look at why that is. This is a graph of mass per particle, mass per proton or neutron, in the elements versus the atomic number of the elements. So remember how nuclear fusion produces energy. You take energy by losing mass. So when hydrogen fuses and turns into helium, you lose mass. So the graph goes down. You lose mass. And when you lose mass, that mass gets turned into energy, and that's the energy that gets emitted to power the star during its main sequence lifetime. Once the hydrogen runs out, then you've got helium fusing into carbon, carbon fusing into oxygen, oxygen fusing into silicon, silicon fusing into iron. Notice what's happening. Every time the core of the star takes an element and fuses it into an even heavier element, there's less of a drop, right? There's a big drop from hydrogen into helium, but there's a very small drop from helium into carbon, and then an even smaller drop from carbon into oxygen, and an even smaller drop from oxygen into silicon. When you take hydrogen and fuse it into helium, you don't have to burn as much hydrogen because you get more energy per reaction. And that's why these stars can live for millions and millions of years burning hydrogen. But once the core has to shift into burning helium, you get less energy for fusing helium into carbon. But you can't reduce the luminosity, right? The luminosity has to stay the same because maintaining that luminosity is what keeps gravity in check, right? Pressure and gravity have to balance each other out. If that star starts losing luminosity, pressure loses and gravity wins. And therefore, if you get less energy per reaction, per helium reaction, you've just got to do more helium reactions per second. And therefore, you run out of helium faster. So that star will burn hydrogen into helium for, 20, 50, 100 million years. It'll only burn helium into carbon for a few million years. It'll only burn carbon into neon for a few thousand years. It'll only burn neon into oxygen for a few years. And it'll burn oxygen into silicon for a few months. And then it'll burn silicon into iron in a few days. Every time you shift gears and go from taking a heavier element to an even heavier element, that next step has to go faster and faster and faster and faster until the core has completely converted into iron. Because once all that silicon has completely converted into iron, iron is the element that has the lowest mass per particle, which means when you take iron and try to fuse it with other iron, when you take iron and try to fuse it into even heavier elements, there's no more energy to extract. You can't take the energy down even farther because after you pass iron, the mass actually goes up. If you take iron and fuse it into something even heavier, you actually have to create new mass. You've increased the mass. How do you increase the mass? By using up energy. So that taking iron and fusing it into even heavier things actually consumes energy, not produces it. Every time you go through a step, from carbon burning to neon burning to oxygen burning to silicon burning, the next step has to go faster and faster and faster. Once that core is completely silicon, the temperature is insane. It's 8 billion Kelvin. And at 8 billion Kelvin, every silicon atom is slamming into every other silicon atom, and they're fusing into iron for the last 2 days of the star's life. It is fast and it is furious. This star is struggling to stay alive. It is trying to take any atoms that it can and slam them into any other atoms to squeeze out the last of the energy until the whole core has turned into iron. And once that core has turned to iron, you can't make any more heat. And if you can't make any new heat, pressure loses and gravity wins. At that point, what happens? You've got the core of the star is a ball of iron gas at 8 billion Kelvin, and gravity has won. And gravity starts contracting down the iron core. And what happens to a gas when you compress it? It's going to heat up even more. So that gravity starts pulling in all the iron. The iron heats up. The iron nuclei actually start absorbing the gamma rays that are bouncing around, because this is still a black body, right? This is a dense ball of iron gas. At 8 billion Kelvin, there is a lot of gamma rays bouncing around the atoms, and those iron nuclei are going to absorb the gamma rays, and it's going to split. When those gamma rays slam into the iron nuclei, it splits the atom into a bunch of helium nuclei and neutrons. And then the helium nuclei get slammed by more gamma rays, and that splits the helium nuclei into protons and neutrons. So this is all happening in fractions of a second. As soon as all the silicon fusion has converted the core completely into iron, gamma rays are now slamming into iron nuclei. The iron nuclei are splitting into a soup of protons and neutrons. And what happens with the temperature? In order to take the iron and split it into the protons and the neutrons, you've absorbed all those gamma rays. You've absorbed energy. When those atoms absorb the gamma rays, the core cools off because energy has been absorbed. Energy has been turned, the energy has been turned back into mass. To take that iron and split it into protons and neutrons, you have created new mass at the cost of energy. So that the core, this photodisintegration is what it's called, when the iron absorbs light and starts disintegrating, that disintegration cools off the core. Well, if the core cools off, gravity wins, pressure loses, and therefore gravity pulls the core in even smaller. And as the core pulls in even smaller, it heats up, creates new energy. That energy gets absorbed by the iron and causes it to collapse even more and even more and even more. The core of that star is now in a death spiral, where gravity is pulling it in smaller and smaller and smaller, denser and denser and denser, and those iron atoms are splitting apart into a soup of protons and neutrons and electrons. Until gravity squeezes these particles so close, those particles are being pulled in so close together that protons and electrons can actually get squeezed together and merge. The protons, the electrons, and some gamma rays slam together and transform into neutrons. This is a reaction, again, that's triggered by the weak nuclear force. And whenever the weak nuclear force changes a particle into another kind of particle, it shoots out another neutrino. This is all happening in a fraction of a second. As soon as that iron core, as soon as all the reactions stop, as soon as all the nuclear reactions stop in the iron core, the core implodes. The gravity has gotten so strong that the core implodes in on itself at a quarter of the speed of light. So that in a fraction of a second, that iron core goes from being the size of a star to being the size of a city. At a fraction of at a quarter of the speed of light, that whole thing, whoosh, shrinks down. and all the protons and the electrons merge together and become neutrons. And instead of being a hot gas of iron, gravity has crunched all those particles down so that that core is now just a hot ball of neutrons. The core becomes what's called a neutron star. It is now an insanely dense, insanely small ball of neutrons. Meanwhile, all these layers of gas up here don't know what's happened. All of this has happened in a fraction of a second, and you've got all these layers of gas that have been floating out there in the outer parts of the star, and then all of a sudden the floor dropped out from underneath them. Right? There is no more hydrostatic equilibrium because the core that used to support the gas has shrunk in a fraction of a second. And so all of these layers of gas here, all of these layers of gas are now in free fall. They're falling in toward the neutron core, and then they hit the core and they bounce. And so now you've got layers of gas bouncing out while there are still layers of gas near the surface falling inward. And you've got these layers of gas falling in and the layers of gas bouncing out, mixing and smashing into each other and swirling together. And so all of these different elements that were so nicely organized, right? Before then, you had this nice onion skin model where you had all these layers of gas that were so nicely organized. And then all of a sudden, when the core collapses down underneath them, all these nice layers of gas are bouncing up and bouncing down and swirling around and smushing into each other. And all these different elements that didn't used to touch are now running into each other. And then the whole thing gets punched. All of these swirling, mixing layers of gas get absolutely punched by a flash flood of neutrinos. All of the neutrinos that got emitted when the protons and the electrons turned into neutrons. When the core collapsed down into the neutron star, it emitted an absolute flash, an absolute spray of neutrinos. And those neutrinos then collide with the gas, and that punch of energy delivered by the neutrinos causes the whole rest of the star to explode. This is what a supernova is. A supernova is where the outer layers of these high-mass stars explode at the ends of their lives. For example, here's a picture of the Tarantula Nebula. This is a star-forming region in the Large Magellanic Cloud, which is a dwarf galaxy that's orbiting around the Milky Way. It's about 170,000 light years away. And all of a sudden, one day in 1987, there was that star right there, minding its own business, and then all of a sudden, boom, the star exploded. Because that star had all of a sudden reached the end of its life. The whole core turned into iron, the iron core collapsed down, imploded down into the neutron star, and all the outer layers of the star exploded. And the hell of a surprising thing is that the thing that nobody expected is that it's neutrinos that caused the explosion. People had been arguing, people had been seeing supernova for centuries. You know, it's like you're watching a star and then all of a sudden a star explodes. And when a star explodes, it tends to catch your attention. And so for the better part of the 20th century, people were arguing about, like, what causes the star to explode? Why would gravity fail? Why would the strong gravity of these stars allow all of this material to explode? And the funny thing is that in 1987, there was this neutrino experiment going on in Japan called the Kamioka experiment. Kamioka was a big device built to detect neutrinos buried under a mountain in Japan. Why would you bury an experiment under a mountain? Because then you have all this rock on top of you to shield particles, right? You've got miles and miles of rock to make sure that the only particles that could possibly touch your detector are neutrinos. I talked before, remember, neutrinos are these tiny little ghost particles, right? Neutrinos have very little mass, no electric charge, they're going at almost the speed of light. Neutrinos are passing through your body trillions of times every second. Yeah, probably trillions of times every second. And they don't touch anything because neutrinos are so small and so fast that those neutrinos can just move through the empty space in between your atoms. And in 1987, there were these particle physicists in Japan looking for neutrinos, and then all of a sudden, a bunch of neutrinos hit their experiment all at the same time. Way more than anybody was expecting. Like, where did all these neutrinos come from? They didn't come from the sun. Where did these neutrinos come from? And somebody says, well, they look like, it looks like these neutrinos are coming from this part of the sky. What's happening in that part of the sky? Nothing. And then a few hours later, the light got there. The neutrinos from the explosion actually arrived at Earth a few hours before the light did. Not because the neutrinos were traveling faster than the speed of light. Neutrinos travel a little bit slower than the speed of light. But because they got a head start. The neutrinos flashed out of the supernova. Some small fraction of those neutrinos actually hit the gas. And then when the neutrinos hit the gas, that caused the gas to run into other gas atoms and trigger new nuclear fusion, and then all of these new nuclear reactions create a flash of light, and it creates the force that triggers the explosion of the star. So about 1 in 1,000 of the neutrinos that got emitted from the core actually hit anything. The other 999 flew out of the star and then got to Earth a few hours before the light did. That 1 in 1,000. 1 in 1,000 neutrinos actually hit anything. And yet there are so many neutrinos bursting out of this core all at the same time that even though 1 out of 1,000 of them hit anything, that is enough. That is enough force to cause the rest of the star to absolutely cause all hell to break loose. And the rest of the star explodes. So that's how we know. That's how we know, finally, after decades of people wondering about it, we know that it's the supreme irony that the brightest, hottest, most violent explosions in the universe, supernova, are triggered by these tiny little ghost particles that under any other normal circumstance just fly right through and don't touch anything. So the supernova 1987A happened in 1987, hence the name. But this wasn't in our galaxy. This was, it was in a nearby galaxy, and it was bright enough that you could see it with the naked eye for a few days. Most of this, you needed a telescope to see the supernova well, which is where these pictures came from. The last supernova that you could see with the naked eye, the last of these core collapse supernova that you could see with the naked eye, happened in the 11th century. July 4th, 1054. And we know, weirdly enough, what day the explosion happened on because there were people there. There were people in the 11th century that noticed, all of a sudden, there was a new star in the sky. Right? The star that died was not very bright because it was pretty far away. The star was 6,500 light years away. So there was just some faint, unimpressive star in the sky in the constellation Taurus. And then all of a sudden, boom, the star exploded. And this star, the supernova, not the star itself, but the supernova explosion, was so bright you could see it during the daytime. It was brighter than the blue sky. It was brighter than the full moon for a couple of weeks. And then gradually, as the supernova starts to fade away, it gets dimmer and dimmer, and then you couldn't see it during the daytime, but it was visible at nighttime for about 2 years. It took 2 full years for the last of the heat and the light to get out of the supernova before you couldn't really see it with the naked eye anymore. So this is why we know what day this happened on, because when a star all of a sudden explodes and it's bright enough to see during the daytime, people tend to write this down. And so we've got documents from the Middle East, from China, and from the Native Americans here in North America of a bright star that didn't used to be there. People tend to write this down. Weirdly enough, there are no extant documents from Europe. There were people in the 11th century in Europe, obviously, and yet, if anybody wrote it down, none of those documents have survived. Probably because it was the Dark Ages, or it's the 11th century. It was the Dark Ages in Europe, and those people that were literate, which wasn't that many, if they wrote it down, the documents haven't survived. But we do have lots of documents from the Middle East and China and the New World. For example, this is one of the canyon paintings from Chaco Canyon. Chaco Canyon is up in the northwest corner of New Mexico, so up near Four Corners. And there's a lot of petroglyphs. There's a lot of cave paintings that the Native Americans around there did. And so I recommend you go, because it's very cool, the cave paintings and stuff. But one of the paintings is this one. What you are looking at is a recording of Orion, because to a lot of the Native Americans of the Southwest, when they looked at Orion, they thought it looked like a giant hand. The mental image of Orion wasn't of a person, they thought it looked like a hand, where the belt of Orion was the wrist, and then the legs of Orion were the fingers. And so to them, that's what they called Orion. They called Orion the hand. Here's the crescent moon, and there is the supernova explosion. And it really was that bright relative to the moon. And so this is a calendar. When was Orion, the crescent moon right above Orion, and the supernova, when were those three things in this alignment at the same time? And the day is July 4th. Right? The moon moves pretty fast from day to day. So the moon was only right there while the supernova was happening on one day, July 4th. So this is how we know to the day when the supernova blew up. When you look at the supernova today, 1,000 years later, you get the Crab Nebula. This is what happens after a supernova. This is not the nice, peaceful puffing out. This is not the nice, peaceful expansion that gives you a planetary nebula. This is an explosion. From the center, that star exploded. And all hell broke loose, and all this gas got blasted out, and it's still expanding today. This gas is basically shrapnel that got blown out of the supernova by the punch of those neutrinos, and they are still expanding today. If you watch it's been 1,000 years, and if you watch the Crab Nebula, if you look at pictures of the Crab Nebula over the last 50 years, it's gotten a little bit bigger, because this gas is still expanding, and it'll eventually blow away. It'll eventually blow away from the neutron star at the core. You can kinda, sorta, almost make out the neutron star. One of these little specks, I think it's that one, but it's one of these little specks of light in the very center of the nebula. That's the neutron star. That's the leftover core after the rest of the star got blown away. This is one of the most famous pictures taken by the Hubble Space Telescope. And it was taken by Alison Law. Alison Law was a grad student with me when I was at ASU. She was a few years ahead of me, so it's not like we were, colleagues or anything. But and her advisor, Jeff Hester, was one of the main guys working on the Hubble at the time, and he was one of the main professors at ASU at the time. He has since gone into partial retirement. Jeff taught for a little while at MCC, which was pretty cool, and I think he's finally decided that he likes retirement a lot. So, but yeah, it's a product of the greater Phoenix area here. The very cool thing about knowing when the supernova happened is that we can say, well, we know it's been 1,000 years. Some of these objects out there in the universe are so old, but we don't know how old. Are they 1,000,000 years? Are they 20 million years? We don't know. They're just old. It's a rare thing to know that we know exactly how old this nebula is to the day, so that you can say, well, if it's gotten to be this big after this many years, how fast is it moving? And you can figure out that this gas is still expanding away at like 1,500 kilometers a second. 1,500 kilometers, that's about 1,000 miles? 1,000 miles. This gas is still, after 1,000 years, this gas is still expanding outward at 1,000 miles a second. And at the very center is the neutron star, what's called the Crab pulsar. Pulsars are a type of neutron star, so we'll talk more about neutron stars and pulsars next time. But in the visible spectrum, they're pretty hard to see, because what is it, right? What is the neutron star? A neutron star is the core of the star. It used to be iron, but it's not iron anymore. It's just a ball of neutrons that has been crunched down to being very small and also very hot. So that even though these neutron stars are insanely hot, they're so small, they have such a tiny luminosity. Right? Unless I tell you exactly where to look, and even if I do tell you exactly where to look, it's hard to make it out. You can't exactly see right where the neutron star is in the visible spectrum. All this hot gas that got blown out of the supernova is much brighter, much higher luminosity than the neutron star itself. Even though the neutron star is very hot, it's not terribly bright in the visible spectrum. The nice thing about neutron stars is that they also tend to be giving off substantial amounts of radio waves and X-rays, so that if we were to take this picture, let's say, in the X-rays, that neutron star stands out like a lighthouse. And we'll see that next time. I'm going to hold you in suspense until then. That's the story for stars that are up to 20 solar masses. For stars, if a star is born with between 8 and 20 solar masses, it is destined for the core to collapse into a neutron star and the rest of the star to explode as the supernova. If the star is born with over 20 solar masses, gravity wins completely. When that iron core collapses, if a star is born with 20 solar masses, then its iron core is so high mass, nothing can stop its collapse. Once the nuclear fusion has stopped in the core, pressure loses, gravity wins completely, and gravity implodes the core down to a single point in space. The collapse doesn't stop at a neutron star. The collapse keeps going past the neutron star until all the mass of that core has been collapsed down into a single particle. And that particle is what we call a black hole. So that's what a black hole is. A black hole is an object that gravity has collapsed down so small and so dense that the gravitational field, the gravitational pull near the black hole is so strong, nothing can travel fast enough to escape it. Not even light. Light is the fastest thing in the universe, And if you get too close to a black hole, the gravitational pull is so strong, even light itself doesn't move fast enough to escape gravity. That's why they're called black holes. We'll talk more about black holes after we talk about neutron stars next time. So that's when things get that insane, when gravity and density and temperature become that unfathomably strong, physics gets very weird and very cool, and we'll talk about that next time. All right. I keep giving you these numbers, right? Oh, the star has to be more than 20 solar masses or more than 8 solar masses, and so on and so on and so on. The reason why mass is destiny, the reason why the amount of mass that a star is born with determines how it will eventually die, is all about the mass of the core. A star can only have a core of about 2 or 3 solar masses. And stop at the neutron star phase, right? This is where the math and the discoveries are a little bit at odds, because the math says you can make a neutron star of about 3 or 4 solar masses. The largest mass neutron star we've ever found is like 2.3, 2.4. So what's going on, right? Can you make a neutron star with more than 2.4 solar masses? The math says yes, but we haven't discovered one. So something's up there. There's still some very exotic physics going on that we obviously don't quite have an understanding of. But it's all about the mass. If that star is born with a core of more than, let's say, 3 solar masses, it's not going to stop as a neutron star because the mass is too high, the gravity is too strong. That star is destined to die as a black hole.